Good afternoon, everyone, and welcome to our third session of this SWEEP Expo. My name is Diana Tingley, and I have the privilege of working as SWEEP's Impact Evaluation Manager. We are now 3 years into our 5-year project, and so far SWEEP has developed around 60 new tools and services, products and protocols, all designed to deliver innovative solutions to generate impact, change or difference in the real world. In my role, I get to witness the success of SWEEP's team's work at first hand, through the process of gathering impact evidence and interviewing project partners and stakeholders. It's truly fantastic and inspiring to hear directly about the many ways in which the SWEEP team are helping to deliver change. This session showcases 4 of these innovative natural capital approaches and tools. We will begin with a presentation from Professor Brett Day, Director of Exeter University's LEAP Institute. Brett is the inspiring force behind the development of the groundbreaking Natural Environment Valuation online tool known as NEVO. As noted this morning by Alistair Johnson from DEFRA, NEVO is listed as one of DEFRA's featured tools in its Anchor guidance. That's its Enabling Natural Capital Approaches guidance. Brett's presentation will be followed by a live demo of how NEVO can be used in practice by SWEEP Impact Fellow Nathan Owen. Brett will be available at the end of the session in the breakout room for this talk if you have any questions. We're then going to move on to a demonstration of the state-of-the-art online natural capital information hub known as LAGAS. LAGAS was developed to support the delivery of Cornwall Council's flagship environmental growth strategy through a collaboration between SWEEP and TEVI, with TEVI being an EU-funded programme creating economic and environmental growth across Cornwall and the Isles of Scilly. The SWEEP and TEVI teams who created and delivered LAGAS are based at University's Cornish campus in Penryn. Lead creator, SWEEP Impact Fellow Jonathan Mosdell, will be joined in this talk by Stephen Lowe, TEVI Industrial Impact Fellow, and Edvard Glucksmann, TEVI Impact Partnership Development Manager. This team will also be available in a breakout room at the end. After a short comfort break, we'll be hearing from Exeter University SWEEP Impact Fellow, Michela Faccioli, who will be talking about her innovative programme of work delivering natural capital accounting in practice. She'll present the team's experiences working to deliver this in 2 very different settings. One with South West Water, and the other working with Dartmoor and Exmoor National Park authorities. Michaela will be joined in the breakout room for this talk by Claire Reid, who worked for both Exmoor and Dartmoor National Park authorities at the time of the project, and who is now head of strategy and performance at Exmoor National Park. And our final talk of the afternoon will be delivered by SWEEP Impact Fellows Kit Stokes and Tim Potes, along with Gert Masselink, Professor of Geomorphology, who are all based at the University of Plymouth. They will be talking about their experiences of developing the operational wave and water level model known as OWL. OWL is a forecasting system designed to predict waves, water levels, and wave overtopping hazards at a finer level of resolution around the southwest coastline than has previously been available. This advanced new forecasting tool has opened up a number of opportunities to positively impact on coastal safety, aquaculture, and marine renewable energy. Kit and the team will be in the breakout room at the end to answer questions. You can also watch a fantastic film which explains their work, and you can even sign up to receive your own OWL forecasts. We've got a few housekeeping notes before we get started. This is a Zoom meeting session, so please keep your video and microphone off whenever you are not speaking. If you want to discuss any topics or contact the host for technical help, please use the chat function. You may find it helpful to hide non-video participants by right-clicking anyone who is not sharing video, or you can click on the 3 dots at the upper right hand of their participant box and then click Hide Non-Video Participants to hide all participants without video. So without further ado, let's begin this session with Brett and Nathan's talk about NEVO. Over to you, Brett.
Thank you, Diana. So it's my pleasure to introduce you to the Natural Environment Valuation online tool. I'll be doing that first. In the short time you'll get to see in action, where Nathan Owen, who's worked very hard with me on this project over the last few years, will be demonstrating it live for your delectation. So NEVO, or the Natural Environment Valuation online tool, it's an spatially explicit tool for valuing environmental change. So it's a tool which provides access to spatially and temporally explicit estimates of the benefits that come from the environment or the costs that come from changing flows of environmental services. And there's many situations, I guess, where decision makers might be interested in having that sort of information. It turns out that those of us who have worked in this area for very many years are quite good at this now. We've got very sophisticated tools with which to do it, computer tools which can whir away all night getting these answers out. I guess the real problem is that it's actually not us who work in the ivory tower who have need of access to these tools. So when I put my hand up, that's signaling for the slide to move on, by the way. I'm not waving at everyone. So here we are in a situation where us up in the ivory tower with their fantastic models and tools and high performance computers, and the people who actually need access to information on the values that come from the environment, the costs and benefits of environmental change, are throwing these scraps down. So we might pass down an academic paper written in academic language, inaccessible to anyone who hasn't trained for 50 years in a particular subject. Or if we're very nice, we might provide an equation or two. Or now and again, in my field, we might chuck down a value, and there we have a value. Finally, a value, a cost or a benefit for environmental change that a decision maker might actually be able to use. For those values, it's really difficult to use those, to apply them. You've got a value, it's £10. But what does that mean? What does it refer to? What's the extent of change of the environmental condition? What's its qualities? How many other environmental resources like that are there, which are substitutes or complements? Who's impacted by it? And when we start thinking about that, these values need to take account of, well, what population is impacted by some particular change? What are their characteristics? How far away from some particular spatial environmental change do these people live? And it's not just people, it's changes in the environment can affect both the production side of the economy and the consumption side of the economy. And often what policymakers are faced with is not just the need for a value for some environmental change. They're thinking about a policy which has an environmental impact, and that environmental impact propagates through all these complicated environmental systems to lead to changes in ecosystem services. These are the actual things that we can put values on. So how on earth are people supposed to go about doing that? So the problem that we addressed through this, the project, the ongoing project that is NEVO, is the one to do with land use change. We're thinking about changes in ecosystem services that come about from any number of things which impact on land use. So particularly rural land use, we haven't really engaged with the urban land use problem yet within this project. So we're thinking about rewild, back to natural grasslands or new forests or agricultural policy or development of land or destocking, these sorts of problems. How can we help decision makers in getting access to values and costs and benefits to do that? Well, within the research group that I work in, LEAP, Land, Environment, Economics and Policy Unit, which is closely affiliated and does a lot of work with SWEEP or in SWEEP, we have some very sophisticated tools. This tool is called the Natural Environmental Valuation Suite of Models. And you can see Natural Environmental Valuation Online is the online development of this. I won't go through all these models, but this is sort of really quite sophisticated integrated assessment model, which can look at lots of different changes in the use of land, and those flow through all the different environmental, water and land use environmental systems, and right at the bottom there come out with some changes in ecosystem services that we can attempt to put values on. So this is what we've got access to. This is what we do our sort of research using. And we've used this tool to examine questions of afforestation. Where's a good place to plant new forests? We thought about it about energy futures and plans to expand biocrops, where to put solar, where to put wind, thinking about these trade-offs in the costs and benefits that impact through the environment as a consequence of land use change. And on the right there, it should be slightly blurred. This is the work that we've been doing with DEFRA, using this tool to examine possible ways in which agri-environment policy might change in a post-EU Brexit world. So that's what we've got access to. Our challenge then, which was set to us by DEFRA in the first place, so this project was funded by DEFRA. I owe them a great thanks for providing us the money to do this, and then carried on through SWEEP. It's a national project, but the focus is also on the Southwest as we come into the SWEEP program as well. And what we needed to develop was some online decision support tool. It provides the ability for decision makers to get access to some of this integrated environment and economy modeling capacity, so that they can sort of examine what might happen if they intervene in certain ways, changing land use or changing policies, what happens through the environment, then onto ecosystem services, and then thinking about the values of them. So that was our challenge. And there's many elements to that challenge. It's got to have this integrated aspect. You've got to be able to change a policy, and we've got to flow through the environmental changes that occur through to the ecosystem services. Because land use is so fundamental to so many different ecosystem services, we're dealing with a whole bunch of them. It's got to deal with spatial changes, it's got to deal with changes across time. We needed this to be able to tell you the quantities of change that you might expect from some intervention, but also these important economic values which feed into decision-making processes. It's got to be answer questions like, what if I did this? And answer questions like, well, where would it be best? Or what would be best in this situation? And we've got to be able to do all that interactively, intuitively, and immediately. So I just got ahead and solved those problems. Well, actually, there were a few of us who were involved in this. So there's a lot of people here. There's other people who've been involved, and there's expertise come from many different disciplines. Economics being my own, but we've also got forest people, water people, and soils people, and ecologists, and mathematicians, and well, just from the whole gamut, and then computer scientists such as Nathan in the middle there, who will be talking to you in a minute. So a really massive team effort to develop this tool. I'll give you some basic understanding as to what Nevo is before Nathan takes you into a look through the tool, running it online. It works in essence on a grid. So you have a grid which deals with most of the land use questions here. It's a 2 kilometer grid. So there is a version 1 kilometer which you also use, but that's not the online version. It's a 2 kilometer grid, the Nevo version. And of course, nature is a bit awkward. It doesn't work on a grid. So there are other sort of spatial scales which play out in the modeling. So we have models of hydrological models which work at the level of a basin. And those basins are developed from models where we have data on the flows and the qualities of water, what we call gauged catchments. And you'll notice we don't extend across the entirety of England and Wales. The model is now for England and Wales. There isn't a Scotland extension yet. We might get to that. But at the moment, and we have these hydrological models working over the locations for which we have data. We've since developed models which go into those ungauged areas, and one of the possibilities for extending Nevo. And when we come to the question and answer session later on, I'd love to hear where you would like Nevo to extend it, or the sorts of things you would like Nevo to be able to do. But you first have to know what it does, so we'll keep pushing on. So these are the core spatial scales. And if you look within one cell, well, within one cell, we really treat one cell as just being apportioned into different land uses. So I've picked one cell out there. And at a high level, it's portioned into woodland, agriculture, semi-natural grassland, urban areas, water areas, which give us our total. But of course, within the woodland, there's different types of woodland, mixed forests or coniferous forests or deciduous forests. And with within the agriculture, there's all the different crops and stocking densities, and a complicated model of farming activity or description of farming activity within those areas. And you can come in within the Nevo tool and you can change land. So you can say, well, we're going to take some of the land out of semi-natural and put it into urban. If you were thinking about a development project, what's the impact on the environment and then on ecosystem services? That's the sort of question this tool is designed to answer. Or you could look at a problem of reforestation and think, well, we're going to take land out of particular types of agriculture, or out of arable agriculture, or out of horticulture or something, and take them out of these things and put them into woodland. Actually, horticulture is not a good example, but out of sheep farming or cattle farming, you take them out of those. So those are things you could do, or you can come in and influence decisions. So you could change prices within the tools and see how that works. Okay, next one. Sorry, I'm waving my hand, which might be very confusing. We make those changes. We can aggregate them up to see what's going on in the hydrological models. And this is how it flows through the tool. So at the top there, these policies and climates and prices impact on the decisions of land makers. And we have models in land makers, decision makers, or land managers, not land makers. I'm not certain we've got any of those. So we have farmers and we have forest managers, and they make decisions in response to the changes that happen in prices or policies. And those affect land use, and those flow through environmental systems to affect water and greenhouse gas emissions, they affect recreation, and they affect biodiversity. And the tool turns out information on how those changes have impacted on those. I have details on the different models is available. I'm going to flick through them now. We have a model for farming, which is based on work which was done in LEAP and tells us about agricultural outputs and profits. We have one for forestry, which comes from Forestry Commission's own models of timber yield and response to prices and climate. We have carbon models, which come from Aberdeen School Farm Pool and the Forest Research's carbine model for greenhouse gases in forestry. We have a model from LEAP again. This is one that I've done a lot of work on recreational value and how that responds to changes in land covers and land uses. And we have models developed by the JNCC, which tell us about species richness models, which tells us about how land use changes might affect the richness of species. Over 100 species are modeled, and we tell you something about the richness of those species. Oh, and yes, I forgot the water models as well. Another thing we worked on in LEAP, which tells about water flows and nutrient and pesticide concentrations and how those are affected for land use change. So before I hand over for the main event, which will be Nathan showing you this tool in real time, I better tell you what I think Nevo is and what it isn't. So what it is it's a proof of concept, really. It's that these complex integrated assessment tools that have been developed in the academic community can be made open access, can be made user-oriented, and can be self-contained. So you don't have to be access to data or be a GIS expert or some whiz with computers in order to use this tool. That's what we were trying to prove that we could do. It's also a platform that we hope will develop into the future, so we can bring more functionality in. We're already within Sweep, we're developing functionality that we would like to bring in there, such as responses in floods, responses in pollination services. So more models, more sophistication. We'd also like it that one day one would be able to come in and select between different models. You know, as academics, you might not be surprised to hear, haven't solved all these problems completely. And different groups have different models which give different results. And I think there's a certain amount of being able to be open and honest about those different results and provide those to decision makers as well. And eventually what we'd hope is we have a community of developers working to provide these sorts of access to these sorts of sophisticated tools to help the decisions with the information that's needed when it's needed. So what isn't it? Well, I think the thing to say what it's not is that it's not the right answer to your question. What this sort of tool can do, it can tell you something about the indicative direction, the magnitude of effects you might expect. It's really good, I think, for first pass analysis to understand where you might think about doing things, what sort of trade-offs involved in the sorts of things you might do. But if you're really thinking about putting a policy into effect, then you might need access to the more sophisticated analysis that are possible, but not through an online tool like this. It really allows you to understand and play and get a feeling for what's going on and get some idea of the magnitude. But I think if you're going to do a really significant investment, you would already realize that there's a need to do the more sophisticated modeling. Okay, well, I hope that gives you a good idea of what Nevo is about, where it came about from, and the sorts of things that might be able to do, what it is and what it isn't. And I'm going to hand over to Nathan now, who will show you some of the analysis that you might be able to try yourself.
Thank you, Brett. I'm just going to share my screen. Okay. Yeah, so my name's Nathan Owen. I'm a postdoc at LEAP, and I've been heavily involved in the development of this Nevo tool. And over the next sort of 15, 20 minutes, going to give you a quick demonstration of the sort of things it can do. And by the way, LEAP is www.leap.ac.uk/Nevo. You can also find it just through a Google search of Nevo. When you first come onto the site, you'll see that you have to register for an account, which is free. We just want a bit of information on what you might use it for, just for tracking our impacts. I've already got an account, so I'm just going to log in quickly. And it brings you through into the site. There is an introductory welcome tour to talk you through the sort of orientation of the layout of the website. I'm going to skip that and tell that to you myself. So you can see it's split into 3 parts really. So we've got this toolbar at the top, the map section in the middle, and also the sidebar on the left-hand side containing the spatial scales. The toolbar is really containing the 3 main modes that Nevo operates in. So I'll go through those in more detail in a demo, but we've got select, alter and optimize. And there's also a session button, which you can save projects that you're working on and come back to them later. There's also some useful help and support, such as that welcome tour I spoke about earlier. There's a series of video tutorials and a lot of documentation on the case studies of how Nevo can be used, and also technical documentation about the modeling that Brett spoke about. There's also an email address here, nevo@exeter.ac.uk. If these don't answer your questions, please do get in touch with us and we'll be happy to help. So if I just start off with a map, it works very similarly to other map tools you might be familiar with. You can pan around, you can zoom in and out on the right-hand side here with these plus and minus buttons. You can also use the search bar to zoom down to a certain area of interest. So I've come down to Exeter here, where we're based at LEAP at the university. And you might want to change the background. So at the bottom here, there's a series of map layers you can add and turn on and turn off. So as an example, you could put in the Ordnance Survey map, or perhaps a satellite image. I'm going to stick with the OpenStreetMap, which is the kind of default. For the scales on the left-hand side, you can see they're all listed here. We've got the 2-kilometre grid scale and the subcatchment scale that Brett spoke about. They're the key spatial units we work on. But you can also work on higher or larger regional scales. So if I just zoom out slightly, you could work with national parks. So you can see Exmoor and Dartmoor there. You can work on local authorities, government office regions. So the main example I'm going to use today is the Southwest, as we're at the Sweep Expo, all the way up to country scale. So you can see we have England and Wales are the largest spatial units you can work at. So each one of these red areas here, these red outlined areas, is selectable, and you'll see we're in select mode at the moment. So in a minute we'll see those, we'll click on one of these areas. So select will tell you, will display outputs from our models, predictions from our models under the baseline conditions, the sort of default parameter settings of the model. Alter then takes that a step further by allowing you to change some aspects of what's going on in that baseline. So as Brett mentioned earlier, you can change the prices. You might also want to change the land use. You might want to convert some farmland to woodland, for example, and see the sort of impact on ecosystem service provision. Optimize goes a step further again, and that you can pose kind of what's best questions. So things like where's best to plant trees to optimize some particular aspect of ecosystem services. So you might want to plant trees, for the best places for greenhouse gas sequestration. We'll see examples of that working later on. So if I jump into an example of a select, I'm going to come down to Dartmoor and switch to the 2-kilometre grid scale. If I just click on one of these cells here, you see that opening up on the left-hand side here is this panel. We call it the details panel. This is where all the outputs and predictions from the models will be displayed throughout the tool. You see it's organized into different tabs. So you have the one I've come onto here is the info tab. So this is kind of stuff like the land cover, those 5 land cover categories that Brett spoke about, and some of the major kind of values and quantities from across the modeling suite. If you look at the other tabs there, you see they're organized into different ecosystem services. So things like agriculture, timber, carbon, recreation, biodiversity and water. But the final one being an export, so you can download some of the data you're seeing displayed here. And going into those individual tabs will give you more detail on that particular ecosystem service. So as an example here, you're seeing some of the key values and quantities. You'll see that they're actually displayed in flows per year in this decade. So they're in the 2020s. So they're predictions from the model of the future, what might happen. And we can flick through 4 decades out to 2050. Another way to view those 4 decades is by clicking on a certain variable of interest. So this is farm profit in this 2-kilometre grid cell. You see it's falling across the decades. It's just a simple graph to show you how that might change over time with climate change. Another way to view the values, and particularly the monetary values here, is switched to annuity mode. So it's taking those 4 decades worth of data and converting them into equivalent annuity figure with appropriate discounting. So to give you sort of a one-off figure that might be used in the cost benefit analysis. So I'm going to switch back to the flows per year mode. So as I said, these individual tabs can give you a little bit more information about what's going on in a particular area, and I've switched to the agriculture tab. This particular cell you can see is nearly 200 hectares of farmland within the cell. Most of that is devoted to agricultural grassland rather than cropland or arable land. And as you might expect, a lot of that in Dartmoor is permanent grassland and rough grazing land, and primarily devoted to livestock, and particularly sheep here. That then feeds through to food production and also farm profit per year. And again, you can view those in flows per year in particular decades or as an annuity. Another example might be the water models, the hydrological information going on in an area. You'll see when I've clicked on the water tab there, we've seen something happen on the map on the right-hand side here. So this is now the overlap between the cell that we're looking at, the cell we're interested in, and the hydrological information in the area. So these are 2 subcatchments. They're actually part of the River Dart catchment. So that is shaded there. And you'll see it doesn't quite extend to the coasts. We've got these gauged catchments flowing up to a particular measurement point. But it shows you that, you know, the stuff going on in the cell not only has an impact on these 2 overlapping subcatchments, but also, as you can imagine, further downstream. And this follow river can kind of tell you how that might happen. So you can see here we're building up a river list down the left-hand side. I'm going to the next downstream catchment here. Alternatively, I can go all the way down to the outlet point. So the basin outlet reached there. So that's the last point at which we have data. And for any one of these, you can view the hydrological information. You can do that by clicking on View Details. And yeah, you can see some of the stuff like percentiles of flow, mean flow and volume, dissolved oxygen concentrations, nitrate concentrations, phosphate concentrations. So some of the water quality information as well, pesticides, and all these things change through time with land use change and climate change. So if you're interested in a particular area, you might want to add it to your current session, and that's what this plus symbol does here. And you'll see that if I open up the session on the right-hand side, this particular cell 85189 has been added to our session. So that was a select for a 2-kilometre grid. It can equally be done for a larger regional scale. So if I just come out to the southwest region here, I'm still in select mode, so I can still select that area. It opens up exactly the same details panel as before, organized in exactly the same way, except this time the information is aggregated. So this is taking the information from all those 2-kilometre grid cells within the southwest and adding up the information. So you can see the land cover is much larger numbers, and the southwest is dominated by mainly agricultural area. Second would be urban, third would be woodland. And again, the main values and quantities are aggregate information from all the different cells within the southwest. The only additional thing you can do when you're looking at a region is actually map the output, and you do that by clicking on any value or quantity you're interested in. So I'm going to have a look at woodland here, and it just colors in those individual 2 grid cells from white to black, depending on how much of the thing you're looking at is going on there. So you can see these darker areas where they're more heavily wooded in the southwest. So things like the eastern side of Dartmoor, some parts of North Devon, and also south of Dorset as well. And you can do that with any one of those values you might be interested in. So I'm going to add that to my current session again and open that up. So you see that's been added to the list of the things that we're looking at during my current session. So that was select mode. I'm going to skip across to alter now. So I'm going to want to change something that's going on in the southwest. So you see I've clicked on alter on the top. I've selected the southwest again. We've now got a different panel coming up on the left-hand side. So we sort of guide you through the process of making an alteration so that you don't make a mistake. So the alterations that you can make are changing prices, and you might want to change crop prices and see how the farmer might organize their farm differently. The one I'm going to do as an example here is changing land cover. So those 5 categories of land cover we saw before, you can directly change them to whatever you want, as long as the total hectares adds up to the correct amount. So what I've done there is add 100,000 hectares of woodland and subtracted 100,000 hectares from agriculture. And we want to know a little bit about where you want to put that woodland in this example. So you can imagine a spectrum from where scarce being putting the woodland in areas where there's no woodland already, to where plentiful being expanding around current woodlands in the southwest. The middle ground being kind of a try and scatter the woodland across the southwest as evenly as possible. So I'm going to look at a where plentiful example. So those changes are now locked in. The only thing left to do really is to select the models that you want to run. You can see agriculture and forestry are run by default. I'm going to also add on greenhouse gases and the biodiversity models. You can add all the models, it will just take slightly longer to retrieve the result. As additional model options, I'm going to skip over those and leave them at their default values. Quite interesting though, on a regional scale is the maps, as we saw the woodland map before. If I select woodland here, we're going to see a map of where that woodland has gone in the southwest. And as another example from biodiversity, we can have a look at the total species richness and how that's changed from before, from the baseline with the woodland planting. So all those changes have been locked in. I'm going to just give that a name so that I know what I've done. So alter woodlands plentiful. And now I've clicked run. The models are now running in the background. They've taken that land cover change from the top there, changing agriculture to woodland. It's now rerun all the models, or the greenhouse gas and biodiversities as extras. And the results come back to you in the same details panel as before. And also it's added to your session. So you can see on the right-hand side there, I've opened up the session panel and we've got the altered site there. So we've got the same details panel as before, but this is now an altered version of the southwest. The only difference being that you've got your original values there displayed, your new values, and the difference between. So this is just confirming that we've added in 100,000 hectares of woodland and taken 100,000 off of agriculture. The little map icon is what we requested from before. So we're now seeing where that woodland has gone. It's in terms of a percentage change from before. So you can see that these green areas where there's been more than 25% increase in the woodland in an area. So you can see they're sort of going around those areas of woodland we saw before, like the eastern edge of Dartmoor, and also some southern parts of Dorset. All the values and quantities work in exactly the same way. There's sort of, you get the original value, the change from before, and the difference between them. And you can see if they've gone up or down. So we've taken away some farmland. We've obviously got a reduction in the farm profit, but we've got a big increase in the greenhouse gas sequestration value. So we've got rid of this farm emissions, but we've also added to sequestration by planting trees. So that's showing you how that's changed. So that's an example of an alter. I don't think I have time to go through and optimize real time, but I can show you how a session might work. So I'm going to open up the previous session that I've prepared. So the Sweep Expo demo. And you'll see it being populated on the right hand side there. So we have these sites I had before, the cell, the Southwest, the altered version of the Southwest. I've also chosen to optimize this area by planting the same amount of woodland, so 100,000 hectares, but trying to target or trying to maximize greenhouse gas sequestration, and also trying to maximize biodiversity, species richness response. So opening those up. And actually the session panel is a really nice way to compare different scenarios. So if I come across to our original alter, it's just showing you where we put the woodland in the first case. And switch across to our woodland optimized for greenhouse gases, you see that the woodland's going quite a different place. So we're seeing a lot of woodland, I guess, on the Devon-Cornwall border there. And finally, the one for biodiversity. Again, it's in a different location. So we're looking at sort of the north coast of Devon and Cornwall, and also some areas of South Devon as well. So I think I've probably got to the end of my time. That's shown you a small amount of what Nevo can do. So we've seen an example of the select, alter and optimize, and had a look at the scenario for woodland planting in the Southwest, and shown that you can really get different areas depending on what ecosystem service you're targeting. So I think I better leave it there. Me and Brett are around now for some questions if there's still time. If not, Brett will be around at the end of the day in the breakout session for a sort of extended Q&A. Thank you.
Hi everyone. I think actually we've decided that we might not have time for questions just at the moment. So we're going to put that opportunity for asking questions of Brett and Nathan back to the Q&A session, the breakout session at the end, which is 4:45. Thank you very much, Brett and Nathan, for explaining simply and eloquently the complexities that are Nevo. It's time now to move on to our next talk. So we've got Jonathan Mosdale and Stephen Lowe and Edward Glucksmann are going to be talking about the LAGAS Natural Capital Information Hub online tool. I'm going to hand it over to you now, Jonathan. Thank you.
Thank you. I'm going to hand straight over to Ed, actually, just to give sort of 5 minutes introduction to the development of LAGAS. Thanks, Ed.
Thanks, everyone, and thanks for the excellent session before this. My name is Ed Glucksmann. I'm a business-facing manager on the TEVI program, and the TEVI program over the past 3 years has been very much the driver of LAGAS, the development of LAGAS, and a lot of the data that's currently going into LAGAS, but not all, of course, comes from the work done with SMEs by the TEVI program. So next slide, please. And I work at the University of Exeter alongside Steve Lowe, who you'll hear from in a second, and Jonathan as well has a long history with the university. So, but it is important to note that TEVI is, of course, delivered in partnership with 3 other organizations, namely Cornwall Council, Cornwall Development Company, and Cornwall Wildlife Trust. Next slide, please. So just as we go through this presentation, if you could, if you have a browser open or a second monitor, if you're lucky, navigate over to lagas.co.uk, because I think it's a lot easier to grasp what the website is all about if you have it in front of you. But just to say that if we go to the next slide, please, LAGAS really represents a culmination of displaying environmental data linked to Cornwall and the Isles of Scilly, very much in the wake of Cornwall's environmental growth strategy, which has been around since 2015 and is currently actually being rewritten and redeveloped. So there'll be a new draft out in the next couple of months. And I think that some of the data that's been acquired is going to feed into that, because the first edition, which you can download from Cornwall Council's website, is very much a blue skies, quite a broad overview. So you're going to get more specifics in the new iteration. And so LAGAS brings together these data from some previous and also concurrent projects. And it also brings in project partners from a number of other programs. And very important from the TEVI perspective, we've worked with over 350 SMEs over the past 3 years or so. And some of the data, in fact, a lot of the data featured on LAGAS comes from those SMEs, sensors and cameras littered across the county based within these SMEs. And that's very much at the heart of what we're trying to do, which is this SME-driven approach to environmental data and environmental growth. And so if you go to the next slide, you just see an example of a typical opportunities map. On LAGAS, you'll get all the details in a second about how that works. But the series of maps all have sources that are that differ, and you see that across each map. So it's very much bringing together a number of projects, a number of programs, and also all of these SMEs that we've been working with, because at the heart of this environmental growth strategy is this link between environment, economy, and local communities. So trying to show that link, which is the sort of foundation of environmental growth, is very much at the forefront of LAGAS. Without further ado now, though, that's just an overview. You're going to get all the details from the next two speakers. And if I could turn it over to my colleague, Steve Lowe from TEVI. And Steve is someone who's worked not only with our 350 SMEs, but also, of course, at the Environment and Sustainability Institute at the University of Exeter. So he has perspectives from the academic and the business side. So over to you, Steve.
Thanks a lot, Ed. Yeah, as Ed says, I'm one of the Industrial Impact Fellows on TEVI, based at the ESI and the Penryn campus for the University of Exeter. If we go on to the next slide, please. So as Ed mentioned, one of the key areas really of LAGAS is to bring together different data sets. So that may be from University of Exeter or other universities' projects. It may be from Cornwall Council in our case, because LAGAS covers Cornwall and the Isles of Scilly. It could be from any other group, like a wildlife trust. So what we really wanted to do was to get as much interoperability between different data formats as possible. So really baked into LAGAS was this idea that no matter what your data is, we aiming to have compatibility with it. So if you use ArcGIS, QGIS, if you like to do your GIS through R, or maybe if you just have KML files, perhaps from an SME, from a business which is not in the academic sphere, hopefully those can be integrated into LAGAS, and that was part of the design. A brief note about some of our sensor networks. So a key part of TEVI is actually being developed by a colleague of mine at the university, and that's this network of sensors. So we're looking at environmental sensors, but also sensors within businesses, looking at issues like electricity use, water use within businesses, to improve the circular economy aspects of businesses. And a key part of this is the development of a LoRaWAN network. So next slide, please. Yeah, so these are just a few of these that we've actually installed. Well, Kyle, my colleagues, installed across the county. So the intention is that these are going to be up and running soon. They've been a bit delayed because of COVID, so he's not been able to go out into the field. But I think he's got quite a few of these already established, and they're developing this really cutting edge LoRaWAN Internet of Things network across the county, which should hopefully spur on some really interesting environmental data exploration across the county and add to our environmental intelligence. Before we head into the website and the demo, just a quick message, a bit of an advert here for Jonathan for tomorrow. tomorrow afternoon there's another session where Jonathan's going to be presenting with Pip from Cornwall Council looking at policy applications. So that's into tomorrow's session for the Sweep Expo. And without further ado, I think Jonathan's going to share his screen, and we're going to explore the website. Hopefully there isn't a there we go. Okay, so this is the home page. I'm very proud to say this was designed by a Cornish design studio in Truro, Bitumen, Cornwall. There's three main sections of Lagasse. There is the mapping section, which we're going to focus on. There's also a live feed section, which is under development, and a resources and links section, which includes links to resources such as the environmental growth strategy that Ed mentioned, to allow people to engage with that, no matter whether they're in a business, academia, or at home. So if we jump into the maps, first of all. So here we are, we've got the initial map screen. We've got these categories down the left-hand side. We can customize these very easily. In the top right, we have a feedback button, which the emails actually go to me, but allows us to get feedback from users. We've also got a login system. So by default, you don't have to log into Lagasse, but we can create accounts for sensitive data. But if we have a look at some of the maps, first of all, we've got this one regenerated with Cornwall Council. This is a map of the Cornwall Sustainability Award winners. So it really shows us that you can have economic data as well as environmental data on the platform. It's really well suited to that sort of thing. And another one is this business locations map. So this is something we're developing, looking at the intensity of jobs across the county. So looking at the centres of the economy, this is the idea is it's going to form the backbone of some work looking at flood risk to the economy. So again, showing the link between environment and economy there. So next one, we've got we're going to some light maps. So these are really interesting to show the different applications of Lagasse, including the different layers there. We've flicked through emissions and sky glow, and also the information box, which is really useful because then you can put all your method information in there. And also there's a little button at the bottom there, which is you click that and it takes you to a PDF with more information. That's really useful for embedding that information in there. We've got an urban change map as well, which Jonathan's demoing here. So this is really interesting data set because it shows the change of across the county over time since 1984, I think that is, and particularly in the China Clay area there, just north of St Austell. Really see the changes in vegetation there. That's really interesting. And the urban development around Truro is quite pronounced in that map as well. And then another interesting data set is this landscape popularity data set, which is generated by social media interaction. You can really see the emphasis on Penwith there, where people have sort of geo-tagged photos on social media of those really popular areas. And it's a really interesting way of exploring the link between tourism and the environment. I think we've got an ecosystem services map, and really this is indicative of which parts of the landscape contribute to a variety of natural services and risks. And a really good example of showing multiple layers of data. So we've got all these different data sources here. So it's really quite a data-rich map, this one. It's generated from sweeps data. So I think actually I hand over to, speaking of sweep, hand over to Jonathan.
Thank you, Steve. So I'm just going to concentrate a little bit on these final maps, and these are probably the most policy-facing maps, very much informed by the needs of Cornwall Council and developed very much in response to them. And these range from everything from attempting to assign a landscape value to the whole Cornwall in this case, identifying those areas which are either under current protection or could benefit from additional protection. And this forms basis of, we can pull out another version of a map that actually attempts to identify connecting corridors between these most valued sites. And hand in hand with that, we'll talk a little bit later just about the exact methods, how this is done. We also developed a number of habitat opportunity maps, really identifying which areas of Cornwall the creation or the restoration of, in this case, 3 distinct different habitats might lead to greater biodiversity or indeed ecosystem service benefits. And you can see it's informed here both by the existing woodland network and also various other data layers that go in to inform this. In this particular case, we've chosen to exclude any sort of woodland planting on existing protected areas. There's various other factors included in it. But this is a way, sort of strategic view of where woodland planting in Cornwall might generate the greatest benefit, at least at this wide strategic scale. And oops, get the right one. There we go. Just to explain a bit how these maps all interrelate, we've mentioned the ecosystem services maps, and these and many other data sources, which I'll talk about in a bit more detail in a moment, go on to influence both his existing nature network maps, that is the most valuable current locations in Cornwall in terms of biodiversity and ecosystem services, and also habitat opportunity maps, where creation of additional habitat might produce the greatest benefit. And from this, we also derive additional maps. There's a draft nature recovery network map and a net gain strategic zone map. So just very briefly, go a bit more information. So this is a version on Lagos of Cornwall's nature recovery network. Again, it's very easy just to simplify a bit by clicking off some of these layers. So this really identifies that sort of dark red areas, the existing nature network, most valued areas that currently exist. Most of these areas will be already semi-natural habitat. And then the green, the purple and the blue identifies potential areas for habitat restoration, with some additional linking corridors also identified. And very commonly we find these actually follow the water network, which is probably no surprise given the distribution of, for example, woodland in Cornwall, which often follows some of these sort of river valleys. And in a way, often the most simplest way to actually improve connectivity would be to improve the habitat along these water courses. So I mentioned also, this went on to inform a tool currently being used by Cornwall Council, and it's a net part of their biodiversity net gain tool. And it really is just dividing up Cornwall into 2 separate zones, really. So it's always zone 1, it's all explained here really, which is the existing network area where we're definitely trying to sort of discourage any sort of further development, or certainly require much higher biodiversity offsetting if there was development in these areas. And zone 2, in a way you want to both discourage, but also these might actually be areas where some of the biodiversity offsetting spend might be targeted towards in terms of habitat restoration. So that's just a very quick overview. I'm just going to stop sharing now and just explain in a little bit more detail some of the methods behind particularly these latter maps and how they were produced. So I'll just stop sharing there and hopefully we'll now go to, yeah. So yes, just to give a little bit of information about the mapping methods and the approach to them. So we have the next slide. So as I hope you get a feel, there's a number of different objectives in a way to the Lagos maps. They're both demonstrating potential applications of available data, informing both sort of general and more specialist interests. But I'm just going to focus here on those latter ones which I demoed, which are more to inform particularly Cornwall Council and AONB policy and strategy development. So again, just to emphasize, a number of maps interact with one another. So I'm just going to look at these 2, the existing nature network maps and the habitat opportunity maps that are both developed in quite a similar method. And just to emphasize, this is a prioritization process. We don't do any attempt at monetary evaluation in these maps. We really are just trying to address these questions of which areas of Cornwall most important in terms of existing biodiversity and ecosystem service provision, and which areas might give the greatest strategic benefit if it was habitat restoration or creation there. So for this, we've used a zonation mapping system. Now this has been widely used probably over the last 10, 12 years, particularly for expansion of existing protected areas, particularly in Scandinavian countries, but also Australia and many other parts of the world. I'm not going to go in great detail. It's well documented, and in a way that's one of the reasons we chose it. But just to underline, it takes spatial data from many different sources. These might describe the benefits of habitat restoration, the biodiversity value of existing habitat, possible constraints or factors affecting the suitability of habitat creation. For example, in Cornwall, we've actually weighted it quite highly by wind exposure, as we consider it quite an important factor when it comes to woodland success in Cornwall. And these layers will also be weighted, and that might be a reflection of their importance, or it might be a reflection of how reliable we consider the data. There's also a number of method parameters, and these in particular, for example, will guide how much importance is given to factors like connectivity across new habitats. And from this, we produce maps, the whole landscape effectively gets ranked. The resolution for maps on Lagos is 100 meters. And from that, we can then extract the most highly ranked areas, just to highlight those areas where we think the greatest strategic benefit would be. And just give a very brief idea of the types of data going into this. Within each category, there will obviously be many different data sources. We tend to use only publicly available data. For example, a dominant land cover might make use, well, it makes use of all the major current sources of land cover data, both those specific to Cornwall and nationally. And from that, we sort of derive our own, if you like, land cover mashup. So I won't go into much detail. In a way, zonation works the opposite of what you might think. So it actually starts, if you were looking, shall we say, asking the question of which areas of Cornwall might benefit from additional protection. It would actually start off, if you like, the concept of the whole of Cornwall protected, and then gradually remove areas that it considers the least valuable. And similar logic works for the actual habitat opportunity maps. And it sort of ensures that the core areas, those areas that last removed, which normally we define as existing habitat or existing protected areas, actually inform the connectivity of the whole network. And just what does it consider? What factors does it sort of consider when determining how it removes cells? These will be the relative weightings given to the different data layers. It will be the diversity of features. So they'll tend to favour cells that might not only be of semi-natural habitat, but also that contribute the greatest ecosystem services. And it also incorporates connectivity. At its simplest, this would be just a simple parameter to comparing the edge to the area ratio of remaining cells, but it can be more sophisticated methods. So really, I just wanted to underline that Lagos, the maps on it, it's not really an automated algorithm. It's very much a sort of process. A number of key decisions inform the generations of map. And that's everything from a choice and the sourcing of the data, land cover data and classification, as I mentioned, connectivity as well, and how much importance is given to that. Also, just simple areas such as the size of the opportunity and network areas that are highlighted. And we tend to, for the habitat opportunity maps, for example, we tend to relate this to the existing habitat found in Cornwall. And also definition of a core and excluded areas. So for wetland, the core area might include a wide range of associated habitats as well as wetland areas. In effect, Lagos really just emphasizes it is very much in development. We expect the maps to change both in response to the key stakeholders on Lagos, Cornwall Council, Cornwall AONB, and also as methods improve and new data comes online. So we'd really welcome any thoughts about improving usability or access to Lagos. And I think at this point, really, I'll just hand over to any additional questions you might have, if we still have 5 minutes.
Thank you, Jonathan. Thank you, Jonathan and Steve and Ed for that. And also I particularly enjoyed the contribution of your cat, Jonathan. It's a great moment. We are just on the edge of having a break, and Jonathan, if it's okay with you, it's been suggested that we move questions through to the breakout session at the end. So if that's okay with you, Jonathan, I'd like to suggest that we do that. Thank you. I think Jonathan has mentioned very clearly and well, and Stephen Ed, that tomorrow afternoon, Philippa Hoskins from Cornwall Council and Emma Browning from Cornwall Area of Outstanding Natural Beauty will be speaking directly about how the Bagasse work is feeding into their programmes of work. That's in the landscape management scale approaches session tomorrow afternoon. So get to hear straight from the horse's mouth what impact work is developing from this fantastic natural capital information hub. So now we're going to go into a little break. We're due back at 3:45, so that's just under 15 minutes. Time to get the kettle on. Please stay logged in, and we'll see you again shortly. Thank you. Hello again, everyone, and welcome back for the last part of this session. I'd like to welcome Michaela Faccioli, who's going to talk about some very different and contrasting applications of natural capital accounting to South West Water and also to Dartmoor National Park and Exmoor National Park authorities. As mentioned before, Claire Reid will be joining Michaela in the breakout room at the end of the session, and to answer any questions that you might have about the work that she's going to be presenting on. So now I'm going to hand over to Michaela.
Thanks, Diana, and good afternoon, everyone. My name is Michaela Faccioli from the Land Environment Economics and Policy Institute at the University of Exeter. And today I'm presenting the results of some recent SWIP work in collaboration with colleagues at Exeter and in partnership with Dartmoor and Exmoor National Parks and South West Water. This presentation will focus on the natural capital accounting framework and will illustrate some practical examples of accounts developed for the South West Water and the Southwest National Parks. So to understand, first of all, what natural capital accounting means, we have to briefly review the underlying framework, which is based on the natural capital approach, which you might have heard about today. At the center of the natural capital approach is the idea that the natural environment and the underpinning natural capital stocks provide environmental goods and services that, combined with other forms of capital, generate something that people enjoy and value. For example, food, timber, clean air and water, recreational opportunities, and much more. A central idea in this framework is that understanding how the environment contributes to human well-being and therefore quantifying its economic value is crucial to inform cost-benefit analysis and appraisals that can better guide decision and policy making around the environment. So without an appropriate valuation of the goods and services that the environment provides, often for free to people, balancing these economic interests and environmental protection is often difficult, and there are clear incentives towards the exploitation rather than the conservation of natural resources. Natural capital accounts are one available tool to inform management decisions by providing in spreadsheet format a snapshot of the extent and condition of natural capital stocks or assets, the resulting flow of ecosystem goods and services provided, and the associated importance or value to people. So within the field of natural capital accounting, most efforts to date have focused on initiatives at international and national scale. The United Nations and the World Bank have led this work by developing a range of international standards and general rules to design natural capital accounts, which have been applied in multiple countries around the world. Only more recently, natural capital accounting has started to be promoted also at regional, local, or organizational scale, at the level of businesses, NGOs, or government departments, which play an important role in land conservation or use. In this context, recent governmental and regulatory documents in the UK have stressed the importance of developing natural capital accounts also at the level of businesses, such as, for example, water companies, or protected areas such as national parks, which own or manage land and can therefore play an important role in environmental conservation. So in this sense, it has been argued that natural capital accounts at local or organizational level can fulfill many purposes, including balancing land use priorities, identifying opportunities, promoting public awareness around natural capital, and providing evidence about the importance and value of the environment to influence policy and funding decisions. However, developing natural capital accounts is also a challenging task for many organizations, which lack the in-house expertise, data, and resources many times, and what is most, a clear methodological guidance regarding how to proceed. So far, the few organizations which have raised to the challenge of producing natural capital accounts have relied on a standard practice approach, which consists in adapting existing methods developed at international or national scale for use at regional or local level. However, large-scale approaches may not be appropriate at local scale and may deliver incomplete assessments of the available natural capital and the resulting stream of ecosystem services and values. Hence, following this approach can be of limited usefulness for environmental management decisions. As part of this presentation, I will focus on two practical examples of natural capital accounts, one developed for Southwest Water and the other one focusing on Dartmoor and Exmoor National Parks. Both were recent SWIP projects. While the starting point in both cases will be the standard practice methodology to natural capital accounting, which I'll review in a minute, in the Dartmoor and Exmoor National Parks application, we went one step further and explored the advantages and limitations of standard practice approaches to natural capital accounting at the local regional scale, and also the implications for management. So to understand what represents the standard practice approach, the starting point is the quantification of the natural capital stocks. In most cases, the standard practice is to identify natural capital asset classes and subclasses starting from publicly available land cover data sets, such as the land cover map data in the UK. So in the table on the right, you can see some examples of habitat classes, for example, woodlands, and subclasses, broad-leaved woodlands, coniferous or ancient woodlands, and so on. The second step consists in quantifying the flow of ecosystem goods and services provided by each natural capital stock. So in the table on the right, you can see examples of ecosystem goods and services that are generally considered in natural capital accounting exercises with information on the metrics used to quantify them. So for example, drinking water is measured in terms of cubic meters of water abstracted, climate regulation is quantified as the tons of CO2 equivalent sequestered, and so on. The last step consists in valuing the identified ecosystem goods and services. This table summarizes some examples of approaches used to value the benefits provided by each ecosystem good and service, ranging from market price approaches, which are used, for example, to value timber, crop production, or livestock, to the replacement or avoided cost approach, which are used to value, for example, climate regulation and air purification, to meta-analysis using the literature, which are, for example, employed to value recreation in some instances. To obtain an estimation of the total benefits, data on the amount of each ecosystem service per hectare of habitat is generally multiplied by the number of hectares of habitat present, and the resulting amount is then multiplied by the per unit value of the ecosystem service. To show you how we went through this process in practice, I've prepared a short video. To create our natural capital accounts, we compile all the information needed in an Excel spreadsheet. We started by recording data on natural capital stock extent based on a GIS analysis, and in specific information on the number of hectares of each natural capital stock class and subclass for the case study area. Then we created a different tab for each of the ecosystem services of interest. So, for example, climate regulation. In each tab, we created a little table like this one to record information on the flow of ecosystem services and their values for each natural capital stock. In each of these tables, we recorded information on the number of hectares of the natural capital stock, so in this case, coniferous woodland,
And in the absence of other primary data, we reviewed the literature to identify multiple estimates of the amount of the ecosystem services provided per hectare of habitat, in this case, tons of CO2 equivalent sequestered by hectare of woodland. Similarly, we also recorded information and multiple estimates on the economic value of the benefits provided by each unit of the ecosystem service, in this case, the value of sequestering 1 ton of CO2 equivalent from the atmosphere. We then multiplied this information all together to obtain the total value of the ecosystem service provided by the specific habitat of interest, carbon sequestration services of coniferous woodland in this case. Because we recorded multiple estimates of the amount and value of the ecosystem services, it is also possible to consider alternative assumptions in these calculations and come up with different results. The same process was then replicated for different natural capital stocks, for example, broad-leaved woodland, all types of woodlands, but also other habitats, freshwater, coastal habitats, etc. We repeated this process for each of the remaining ecosystem goods and services, and as a last step, we aggregated all the information in a summary table like this one, which effectively represents our natural capital accounting table. The rows in this table represent the information by natural capital stock, class and subclass, while the columns refer to information by ecosystem service. And for each ecosystem service, we reported information about both the biophysical information, so the quantity of the ecosystem service provided, as well as the monetary value. The last column on the right reports the values across all natural capital stocks, but also broken down by a stock category and, where possible, subcategory.
So the first case study that I want to present is a natural capital accounting exercise developed for Southwest Water. To motivate this exercise, it's important to provide some background information on the current environment in which water companies in the UK operate. So the UK water sector is not a free competitive market, but utilities are highly regulated to make sure that water and wastewater treatment services are delivered while environmental obligations are met and customers get a good value for money. So to monitor and ensure the achievement of these objectives, every 5 years, water companies have to undergo a price review process where evidence needs to be submitted regarding what has been and will be achieved. In the last price review process in 2019, water companies were asked to plan for new and better ways of delivering water and wastewater services that are both value for money and offer resilient solutions to short and long-term environmental shocks. So our natural capital accounting exercise contributed to this process and is one of the first examples of its kind. The natural capital accounting exercise was developed to provide a snapshot of the anticipated environmental and social benefits of the interventions planned by Southwest Water in collaboration with the delivery partners between 2020 and 25 in the upstream thinking catchments, which are illustrated on the map. And you might have heard about that already from David Smith this morning. First, we started by collecting the data for the accounts. So each project manager was asked to provide information about the interventions planned in each of the business cases between 2020 and 25, such as woodland management or creation, planned peatland restoration, calm grassland management, agricultural land management, or other forms of habitat management. Then we asked project managers to provide information on the environmental impacts that are expected to result from these planned interventions between 2020 and 45. Where possible, we collected quantitative information, but where this was not possible, we asked project managers to provide a qualitative assessment, a best guess, alongside with an estimate of the uncertainty around the provided information. Last, we reviewed the literature to obtain estimates of the economic values of the identified ecosystem services to quantify the overall private and social benefits associated with the planned interventions. So this table summarizes the types of ecosystem services and benefits considered in the project, which include a variety of public and also some private benefits. We were able to quantify carbon sequestration services using a variety of tools, such as the woodland and peatland carbon codes, the Culm farm tool, etc. And we were able also to value these services using the social cost of carbon approach. We also quantified the expected impacts on recreation in terms of the change in the number of visits and value the associated social benefits by using the outdoor recreation valuation tool, ORVAL. We also managed to value the physical and mental health benefits associated with spending time outdoors volunteering. And for a range of other impacts of the planned interventions, such as improvements in cultural heritage, in the conservation of biodiversity, flood risk mitigation, etc., we only managed to collect qualitative information on the expected directions of change. And finally, starting from expected predictions of the impacts of changes in agricultural and land cover management practices, we monetized the anticipated changes in farm profitability. So this table, which you might have seen this morning, provides an overview of the overall impacts of the various management interventions listed in each of the rows on the ecosystem services, which are listed in each of the columns. Overall, you can see that the planned interventions are anticipated to deliver multiple environmental benefits. More specifically, we then produced another table to summarize the information on the quantity and values of the ecosystem services that are expected to be generated over the period 2020-45 as a result of the management interventions planned for the period 2020-25 across all upstream thinking catchments. So for each ecosystem service listed in each of the rows, details are presented on the interventions driving the change, the expected change in the ecosystem service flow quantified when possible, the net present value in monetary terms reflecting the resulting cumulative benefits over the period 2020-45, and when no monetary quantification of benefits was possible, we provided a qualitative assessment using color-coded arrows. So green means a positive effect on social welfare is expected, red a negative effect, and yellow no effect. An assessment of the uncertainty, low, medium, or high, regarding the reported information was also included. Then we aggregated this information to provide an overview of the total benefits expected to result from the planned management interventions. And as you can see, across all catchments, a significant proportion of the total value is expected to be accruing to farmers due to cost savings resulting from better soil management practices, and the wider society due to increased recreational opportunities and carbon sequestration services. The total figure is about 40 million pounds worth of benefits and needs to be compared with an estimated investment cost of about 10 million pounds. And this suggests that the benefits expected from the planned interventions will clearly exceed the costs. So the evidence produced as part of this project contributed to South West Water's business plan and to the award of the fast track status and funding as part of the last price review process. South West Water was one of the few UK water companies whose business plan was acknowledged to innovatively deliver water and wider environmental and social benefits while ensuring customer value. And SWIP played an important role in contributing to this success. So in the second case study that I wanted to present, we critically assessed the advantages and the disadvantages or limitations, as well as the usefulness for decision-making of the standard practice approaches to natural capital accounting at local organizational scale, taking Dartmoor and Exmoor National Parks as case studies. So at the start of this project, we discussed with key staff members from both national park authorities about their expectations regarding the use of natural capital accounts to inform decision-making. Then we reviewed the standard practice approaches to natural capital accounting, gathered the necessary data on natural capital assets, ecosystem services and values, and replicated the standard practice approaches for our case study areas. We then critically assessed the results, identified some of the limitations of the standard practice methodology, and suggested areas of improvement by testing for the sensitivity of the account results to alternative assumptions regarding the quantification of the amount of natural assets, flows of ecosystem services, and values. Finally, we discussed the results of the project with the stakeholders to assess the degree to which initial expectations and ambitions regarding the usefulness of natural capital accounts could actually be met. So this is a summary of the natural capital accounting results. Following the standard practice, it was possible to quantify and value some ecosystem services, which are highlighted in green, but in many other cases, the quantification or valuation of some ecosystem services was either only partially possible, orange cells, or not possible entirely, highlighted in red. Reasons justifying these gaps have mostly to do with missing data or limited valuation evidence. Based on this, only a partial picture could be provided of the wealth of benefits supplied by the natural environment in the case study area. So what we did next was to discuss the limitations of using standard practice approaches and through some case study tests, offer some improvements in relation to the measurement of natural capital stocks and the quantification and valuation of the flow of ecosystem services. In the interest of time, I'll just present a couple of examples now. So regarding the measurement of natural capital stocks, one first problem identified was related to the limited availability and accuracy of fit-for-purpose data. So in the absence of systematic local monitoring and data collection, the standard practice suggests to use generic national satellite-derived land cover map data to quantify natural capital stocks. However, at smaller scale level, following this approach often implies that locally specific and relevant natural assets are often overlooked. So national data sets are also prone to habitat misclassification at fine geographical scale, and in addition, data are not consistently collected following the same methodology over time. So addressing these problems is crucial to develop more specific, reliable, and therefore useful natural capital accounts. Concerning the measurement of the flow of ecosystem goods and services, one of the major problems identified concerns missing data. For example, following the standard practice, no biophysical information was available to quantify wildlife or biodiversity, which is clearly a limitation, especially when the accounts are developed for national parks. Another problem identified was related to the missing information on the ecological condition of the natural capital assets, which is often overlooked in standard practice accounts, even though ecosystem condition is an important determinant when quantifying the flow of ecosystem services. So for example, peatlands in good condition can sequester carbon, while peatlands in bad condition emit carbon. So very different conclusions could be drawn on the quantity of carbon sequestration services depending on the ecosystem condition. Sometimes the reviewed standard practice approaches rely on a range of alternative methods to quantify the amount of ecosystem services provided by different habitats, and this therefore introduces the question of which approach should be considered. So to illustrate this point, let's consider the case of carbon sequestration services in broad-leaved woodlands. The reviewed studies, listed one per row, provide, as you can see, very different estimates of the amount of carbon that can be sequestered per hectare of woodland, mostly because they consider different tree species or different definitions of greenhouse gases. So depending on the assumptions considered, the amount and the value of climate regulation services are very different, and in some cases they can even be double. Regarding the valuation of the flow of ecosystem goods and services, one of the main problems encountered with the standard practice approaches was the lack of valuation information to quantify the benefits associated with some key ecosystem goods and services, such as wildlife, biodiversity, landscape scenery, and cultural heritage, which therefore could not be included in the accounts. In other cases, available estimates of economic values only represent a partial estimate of the benefits supplied by the environment to people. So for instance, the value of flood mitigation is often equated to the costs saved in flood control infrastructure in the presence of lower flood risks. But this is clearly an underestimation of the benefits of flood mitigation, given that, for example, the value of life saved is ignored from this figure. Another limitation we identified in the reviewed accounts was the lack of consideration of spatial aspects. We know that the benefits that people, next slide please. We know that the benefits that people perceive from nature depend on the distance between the beneficiary and the location where the ecosystem service is provided. So despite these considerations, though, hardly any of the reviewed natural capital accounts included considerations of spatial aspects. To illustrate these points, we take the example of recreation and relied on the outdoor recreation valuation tool Orval to show the role of spatial factors on the account results. Orval, developed by the LEAP Institute at Exeter, as we've heard before, is a complex travel cost model combining detailed information on visitation data and characteristics of the visited locations, such as land cover data and facilities available, amongst others. We started by estimating the recreational values for the national parks using the Orval model, which assumes that shorter distance traveled, more site accessibility, and the uniqueness of a visited location all contribute to increase the recreational value of a given site. Then we compare the resulting estimates with an alternative approach, which doesn't consider spatial aspects, and we show that accounting for spatial patterns produce an estimate of the recreational values, which is substantially larger compared to a case where spatial factors are not considered, as is standard practice in local natural capital accounts. So considering spatial factors in the valuation process is indeed important. The last step at the end of this project consisted in evaluating with our stakeholders the usefulness of the produced accounts to inform management decisions. So discussions evolved around the aspirations identified at the start of the project by the national park authorities regarding the usefulness of the accounts as summarized in this table. Using a color-coded indicator system, we then assessed the extent to which the produced natural capital accounts were perceived to meet the initial aspirations. As you can see, only in few circumstances, which are highlighted in green here, the initial aspirations were met. In one case, highlighted in orange, they were partially met, and in most cases, marked in red, the aspirations were not met. So the stakeholders agreed that the produced accounts can provide a useful structured framework to classify natural capital stocks and value the related ecosystem services. The accounts were also perceived to be partly useful to illustrate some knowledge gaps and information shortages. However, due to the account gaps and sensitivities to the underlying data, it was also felt that the accounts were of limited usefulness to guide management decisions. Due to a mismatch between the expectations of what natural capital accounts can be used for and what they can actually deliver, it was believed that the produced accounts could not help to inform a variety of management decisions, including designing farmer schemes, leveraging new funding, prioritizing between different management options, etc. So to achieve these goals, other tools such as cost-benefit analysis or risk registers represent perhaps more suitable options. So in conclusion now, our work pointed out that natural capital accounting at subnational scale can to some extent be a useful instrument for environmental decision makers. Hopefully we have managed to show that the environment provides a range of benefits to people which can be valued using a range of methods, and that explicitly considering these values can help making better decisions. However, we have also showed that in its current format, there is still a long way to go before natural capital accounts become a trusted and robust source of information to guide decisions. There are in fact a number of areas where natural capital accounting could be improved at subnational scale in the future. So data availability is one of the main limitations, and the collection of locally specific and fit for purpose data should be prioritized going forward. Also, the quantification of the flow of ecosystem goods and services should be better linked to the ecological condition of natural assets, something that has been overlooked so far. Spatial aspects also need to be incorporated into natural capital accounts to better inform decisions about spatial planning, for example. Valuation methods need to be further progressed to be fit for purpose for natural capital accounting, especially in relation to the measurement of complex ecosystem services, such as flood regulation, landscape values, and cultural heritage or biodiversity. Given the sensitivities of the results to the underpinning data and assumptions, being explicit about the uncertainties was also felt to be important. Then, given the need for analytical and technical expertise and skills to develop and update the accounts in-house, publicly available tools developed by specialists but tailored for non-specialists also need to be promoted to support small organizations in the development of natural capital accounts. So this was one of the conclusions that we obtained from both case studies, as for the previous conclusions. And finally, to inform management decision-making, especially at subnational scale, there is a need for a clear guidance on the methodology and for more clarity regarding the capabilities of natural capital accounts in order for these tools to be more useful and informative in the future. Thank you very much.
Thank you, Michaela. That was fantastic and perfectly to time. So we're going to move on to the last talk of this afternoon. So that's 30 minutes from, we're going to hear from Kit Stokes, Tim Potes and Kurt Masselink from University of Plymouth about their experiences developing the operational wave and water level model known as OWL. And then when we finish this talk, we're going to go straight into the breakout rooms. So save up all your questions for them. Okay, I'm going to hand over to you now, Tim.
Thanks, Diana. It's just myself presenting actually, but I think Kurt and Tim are on the call, so they'll be involved in the Q&A session, I believe. My name's Kit Stokes, as Diana mentioned. I'm from the Coastal Processes Research Group at the University of Plymouth, and I'm going to talk to you about local scale wave forecasting, which is something that we've been using to develop some different coastal applications around the Southwest as part of the SWEET project. So I'll start off just pointing out some of the unique features of the Southwest coastline and how that relates to the tools we've developed. I'm going to talk about what local scale wave forecasting is and why exactly we need it. I'm then going to go through the approach we took with developing a wave and hydrodynamic model of the Southwest. And then I'll talk about these 4 case studies we've developed through SWEET. One relating to wave overtopping, or predicting when wave overtopping will happen. One is related to aquaculture operations. One is a marine renewable energy case study. And the last one is a beach hazards forecast. So the Southwest coastline, as we all know, is a very unique place, very beautiful, and it has a lot of unique features about the coastline. So first of all, we have various features like large gravel barriers that protect harbours and infrastructure and properties. We also have the Dawlish rail line that is quite unique to the Southwest region, and that occasionally gets pretty hammered by the ocean. We've also got gravel barrier at Slapton Sands, which is quite unique. It has an A road running across the top of it and also protects a freshwater lagoon, which is a site of special scientific interest. And surprise, surprise, the sea likes to take chunks out of the A road there as well. We've also got a big marine city in the form of Plymouth. And, you know, while there's lots of industry and infrastructure and a naval base in Plymouth, it is generally well protected by the breakwater out there in the Sound. We also have a lot of these small sort of towns and villages dotted around the Southwest, enclosed in small bays, like this example down here, which is Port Mellon on the south coast of Cornwall. And I'll talk a bit more about that, but having those little embayed areas of the Southwest coastline presents various challenges. We also have, you know, historic harbours, ferry ports, big sandy beaches popular for recreation, big sandy beaches popular for families. And up there in the River Severn, we also have one of the largest tidal ranges in the world. In fact, the second largest tidal range in the world. So as you can see, there's a lot of natural capital going on, both in terms of the recreational value and the opportunities for industry and business around the coast, but also in the hazards posed by the natural capital itself. So just to look at that a bit more, you know, as everyone knows, the waves get quite big in the southwest. Sometimes they get very big. They sometimes get really, really big, and occasionally they get ridiculously big. And so not to be outdone by the rest of the southwest, the River Severn, also having this large tidal range, actually gets a tidal bore breaking occasionally, which has been known to attract stormtroopers to visit. So what are we going on about when we talk about local scale wave forecasting, and why do we need it? Well, clearly the southwest region is very wave dominated. It's you know, it has a lot of hydrodynamic features about it, but the waves are probably the most notable feature of the southwest. So why do we need this local scale wave forecasting? Well, let's have a little look. First of all, here is an image of the model domain that the Met Office were using when we started SWEEP to predict waves and hydrodynamics around the UK. So as you can see, it covers a very big spatial area. It's called the Northwest European Shelf Model because it covers that kind of spatial scale. If you can just, sorry, can you just play the, that's it, play the video. There we go. So if we just zoom in on this grid, this is called the AMM7 model, and it actually has a 7-kilometer model resolution, which means that each of these squares has a different estimate of the wave height or the water level or the hydrodynamics happening around the coast on any given day. Now, when you zoom in on the coast, we're looking here at the Padstow area with Trevose Head roughly in the middle of your screen. When you zoom in on the grid, you notice that actually one grid cell is quite large compared to our coastline, and those little pockets that I talked about earlier, the embayments around the southwest, get sort of lost within those grid cells. And what that actually means is that basically we have one estimate of the wave height on either side of Trevose Head there, when clearly one side is quite exposed to the Atlantic, while the other side is actually quite sheltered. And when you come to develop a coastal tool like a hazards forecast, you really need to know the difference between one location and another if there is a marked difference in the wave height. So that 7-kilometer grid resolution wasn't really sufficient when we started SWEEP to create the tools we wanted to create. Now, the Met Office have now changed to an AMM 15 model, which is actually 1.5 kilometers roughly in resolution and looks a bit like this. So in the last year, they've now moved to a resolution which is much more suitable for this sort of local scale application of wave forecasting. However, that didn't exist when we started out SWEEP. So we developed our own model domain, our own hydrodynamic model, and that has a 1-kilometer resolution, which you're seeing now. And as you can see, we've got multiple grid cells on either side of the headland there. So we're definitely able now to differentiate between the wave conditions at one location to another location nearby. Not only that, but we can also get multiple estimates of the wave heights within a single embayment, which means we can determine the difference between a sheltered end or an exposed end of the coastline there using a wave model. If you just press play there, Paul, it should zoom back out. So let's just look at the extent of the model that we created. It's actually a southwest-centric model because it was partly developed for SWEEP. So it covers the southwest, it also covers South Wales. And if you just click through and press play again, this gives you an idea of what the model kind of looks like. Basically, this is an animation of wave height through time. So the model is basically transforming wave conditions from deep water into the coast. And you can see dark colors in red are large wave heights, and small waves would be represented by blue colors. So that gives you a kind of idea of what the wave model looks like. So what was our modeling approach? How did we put this together? Well, we used a model called Delft3D, which is quite a commonly used hydrodynamic model. We set up a 1-kilometer resolution grid around the southwest, and we actually used the Met Office boundary data from their AMM7 model initially. The Met Office are a key partner of ours on this project, and they've been working closely with us to help feed data into our models, but also helping us in the development of our coastal applications as well. So this image on the right shows you the blue square, which is our model domain. The black squares were the original AMM7 model, which had that coarser resolution. And that feeds data in around the edges of our model. And then we refine that information. We effectively downscale the coarse resolution information to a finer scale and transform those waves into the coast. So this runs every day. Here you can see the bathymetry in the model. This is the seabed depth, but you can also see some other features on this plot, which are the little red circles, and they represent the wave buoys that we have around the southwest. We've also got some tide gauges there as yellow diamonds, and those allow us to validate what our model is predicting and actually compare it to what's happening in reality. We've also got little blue lines, which you can see dotted around the coast there. Those represent coastal profiles that are measured regularly by the regional monitoring programme. And having those is absolutely vital because it then allows us to predict what the waves do when they get very close into the coast and start to run up at the coast and cause things like wave overtopping to happen. So this runs every day and it creates a 3-day forecast of the wave conditions and water levels. We then take the output of the wave conditions around the coastline at some shallow depth contours so we can get better information around the coast, and we use some empirical shoaling methods to actually take the wave conditions from the shallow water right into the toe of the sea defences around the coast. And that's, wave breaking, run up and overtopping is actually something that even a 1 kilometre model can't resolve. So once we get to the coast, we have to use different tools. And that's what I'll talk to you about in a moment. And as I mentioned before, we have these 186 profiles in the southwest. We also have some new ones in South Wales, which aren't on this plot, but those profiles allow us to make those computations at the coast. Okay, so this is the southwest region, obviously. We have these 4 case studies I want to talk to you about. The first is the wave overtopping forecast, which we developed in collaboration with the Environment Agency. Now, clearly, having forewarning of when a wave overtopping event might happen is quite useful to the Environment Agency. They have a remit which involves providing protection from coastal flooding. So if they can get forewarning of when waves will be overtopping our sea defences, they can then more actively go out and make sure sea defences are in place and target the exact locations and times at which this flooding may be happening in order to safeguard our communities and businesses. We've recently expanded this coastal overtopping forecast to South Wales, and so we're starting to work with partners there to sort of gain similar benefits for the South Wales region. I'll then talk to you a little bit about a marine forecast that we've developed with offshore shellfish to try and help them with their aquaculture operations in Lyme Bay. We've got a case study at Crantock Beach in the north of Cornwall, where we're basically using our wave information to create a really high resolution beach hazards forecast at one specific beach. And I'm going to talk to you about Bombora Wave Power, who are deploying a wave energy device off the coast of Pembrokeshire, and we're hopefully going to be feeding some wave data to them to help them with their deployment and maintenance activities. So let's go through the first case study then. OWL is the operational wave and water level model. Primarily it is the model domain that I mentioned to you previously, but more specifically, it is the overtopping forecast that the Environment Agency have been using. And our aim for this project was really to improve the information that the Environment Agency had at their fingertips as a storm would be coming towards the coast. And we wanted to improve that information by, first of all, increasing the wave model resolution, which, as I mentioned before, was previously at 7 kilometres, so it was quite coarse and only really allowed them to predict when these sorts of storm events would hit on a region by region basis rather than on a local scale. And we wanted to predict wave run-up and overtopping explicitly. This was not really possible until fairly recently because the models and the equations simply didn't exist until the last 5 years or so to predict wave run-up and overtopping at all sorts of various types of coastal profile. So we wanted to be able to provide overtopping warnings for the various types of coastal profiles we have in the southwest. Obviously, we have sandy beaches, gravel beaches, and we have lots of locations defended by sea defences. And each of these different types of coastal profile requires different models and equations to be able to predict when coastal overtopping will happen. And we wanted to go a step beyond just predicting when waves would be crashing over our sea defences. We actually wanted to be able to predict how much water would be going over and exactly what hazard level that represented to the public or to properties or to transport at the coast. So what is this wave overtopping thing I keep going on about? Well, this is what it looks like in action. This is the gravel barrier at Chesil being overtopped by a large storm wave during the 2013-14 winter. I forget which actual storm this was, but what you're seeing is basically the wave run up, going up the beach and exceeding the height of the barrier, which means that lots of water is thrown over the back of the barrier and is then able to flood properties, as you can see. And this is what we would class as a naturally defended coastal profile. So it's the main line of defense here is the gravel barrier that you can see there. So let's look at a different example. This is Port Mellon and a man-made sea defense. And as you can see, there's quite a lot of hazards going on here. We've got property being flooded. We have a rather shiny Porsche that was almost washed into the harbour. So clearly a hazard to pedestrians, to transport and to property. So very hazardous event indeed. And actually what you're seeing here are some very small waves combined with quite a high tide level. But without the ability to predict the wave overtopping, you would actually not predict that any overtopping would be happening here at all, because if you just predicted tide level, well, there'd be no hazard. But clearly just having small waves at this location was posing quite a big hazard to the local population. So how do we then use that local scale wave information to predict overtopping? Well, first of all, we use a suite of different coastal profiles around the southwest. Here's a map of some profiles in Wales to just give you an example. So we've picked a couple of profiles out of the Regional Monitoring Programme's database, which are those two circled profiles. We then take a close look at what the sea defences look like at each location. So we would describe the type of sediment here. We clearly have a gravel beach backed by a vertical seawall, and you can also see, quite precise features like there's a wave return lip on that seawall. And those pieces of information help us to determine which equation to use to predict overtopping at a given location. So once you have the wave information from the model, you have the information about the coastal profile, you're actually then able to predict through time what the wave run-up level will be and what the wave overtopping hazard might be. So I've given you a couple of examples here. The two plots at the top are from Newlyn, the ones at the bottom are from Perranporth, and on the left of your screen you can see the measured coastal profile, and on the right you're seeing a time series of the predicted water level in black and the predicted wave run-up in blue. And the grey shaded area that you see in the top plot actually represents the seawall, and you can see that on those high tides, when the blue reaches the seawall, you get an overtopping warning happening on the Friday afternoon. And there's an orange symbol to show you when the warning occurs. And that orange symbol also tells you something about the hazard level. So we've classed those into three categories based on the Eurotop manual. And those three categories are risk to pedestrians and property, and risk to pedestrians, property and vehicles. So they're sort of three commonly used thresholds in the overtopping literature, which we've applied here. Down the bottom there, you can see an example from Perranporth, which is actually slightly different because it's basically just a sandy beach that's protecting the town of Perranporth. And so we use a slightly different set of equations to predict overtopping. But there again, you can see that there's a risk to pedestrians predicted on that particular day. So we wanted to test this overtopping forecast out. So we did some model validation. We basically spent the whole of the winter of 2018-2019 looking at coastal webcams. And you can see those stars are where we found a coastal webcam around the southwest, which we could monitor. And we looked at those every day over a whole winter on every high tide. So here's some example images from Penzance. And these images have been sort of subjectively categorized from a low hazard level to a high hazard level based on what you can see in the webcam image. And essentially we compared our subjective classification each day to what the overtopping forecast predicted. We had over 1,000 pairs of observations and predictions to look at by the end of the winter. 9 of our 15 webcam sites experienced some sort of overtopping over that winter, so quite a lot of data to actually look at. And that resulted in 36 overtopping events to base our analysis on. The model did pretty well. We had a 100% hit rate for severe overtopping events, the sort of orange and red categories there. And also the model was encouragingly good at differentiating between low and high hazard events. And in all but one of those 36 events, it actually managed to get the predicted hazard level to within about one level of where it should be. So not a bad result. We were quite happy with that. Okay, so now that we're sort of happy with the model, that's actually been up and running since 2018. We now output the model outputs to the web. You can sign up on the Channel Coastal Observatory website. That's the sort of national monitoring, coastal monitoring website. We have a page on there, and if you go there, you can sign up for different sub-regions around the southwest, and now that includes South Wales as well, as you can see. And what you get when you sign up is a daily email PDF when there's an overtopping event predicted for your sub-regions. So here's an example for one sub-region. You get a sort of regional overview in the top plot there. You also get a zoom in on your sub-region, which is on the bottom left of that image. And then you also get the detailed time series plots for each individual profile within that region. Now we also output the regional level forecast to Twitter. So you can just go on Twitter each day. Our handle is @coastal_hazards. And each day you'll see the regional forecast. You can get an overview, a kind of high level view of where and when there might be hazards from overtopping. Okay, so what's been the outcome of this work? Well, the forecast has been used by the EA since 2018 to inform their operations in the southwest. They have not only been able to sort of pinpoint where and when to send their coastal flooding officers prior to storm events, but that's actually helped to safeguard the officers themselves. They now know what sort of hazard level they might be facing when they go out to a flood event. We have 54 email subscribers, 435 followers on Twitter. You know, and those numbers aren't big in social media terms, but actually they're the people that really count when it comes to this sort of forecasting, because 19 of those emails are going to flood warning officers around the southwest who make day-to-day decisions using those forecasts. And overall, the EA consider this overtopping forecast to be an exemplar demonstration of coastal forecasting, and they've used this as a sort of regional pilot, and actually it's helped to support a funding bid from the EA to get quite a few millions of pounds in order to improve their coastal forecasting, and they're now commissioning a nationwide coastal overtopping forecast. So I'll move on to the next case study then. This is a aquaculture operations case study working closely with offshore shellfish. They're building the UK's first large-scale mussel farm in Lyme Bay, and they have issues sending their boats out under certain conditions. As you can imagine, if the waves are very large or the sea is very choppy, it's quite hard for their boats to go out and work on the mussel farm and harvest the mussels, and that can cost them quite a bit of money. So if they were using their existing forecasts and they decided to send a boat out on a given day, and then that boat ended up having to turn back because the conditions were too rough, that would represent something on the order of £1,500 of wasted money. So our aim for this project was to generate a kind of a detailed forecast that had some bespoke outputs for offshore shellfish, and ideally to reduce the number of wasted trips they have through more accurate marine forecasting. So this is their area of operation. They have 3 mussel farm sites in the Lyme Bay area. And we produce outputs like this using the OWL model. So you can see wave height and wave period plotted there. And as you can see, the model is able to sort of differentiate gradients in the wave conditions from that bottom plot. So they could see that perhaps site number 1 and 2 might have been suitable to work on that day, but perhaps not site 3, because the wave period was a bit longer and the wave energy would have been a bit higher. We also developed some more bespoke outputs for them. So this is an example of the wind and tide induced chop that we predict for them, and they told us that they were having issues when you have these very choppy conditions, not necessarily big waves, but quite choppy conditions, which make it difficult to operate on the farm. And so we've actually used all our hydrodynamic information within OWL to predict whether there'll be low levels of chop or high levels of chop in the water on any given day. Okay, so the third case study is working with Bombora Wave Power, and they're planning on deploying a wave energy device on the seabed just off the coast of Pembrokeshire. Now this is up in West Wales, and it's actually quite close to the boundary of our model domain, but it's well within the domain, so we were quite keen to work with them and see what we could do for them. Our aim here was to inform their wave energy device deployment and maintenance activities by providing them with detailed information about what the wave conditions would be, but also potentially we can help them to understand what the wave resource is like when they're deploying their device and through their deployment period. The device is being deployed at a marine energy test area, so this is all very novel device testing, and they need to know exactly what the wave conditions are going to be doing in order to test their devices in a safe and efficient way. So as I said before, it's quite close to the model boundary, and we wanted to be sure that our wave model was going to be able to give them accurate data. So we did a little comparison to a Wavebuoy deployment they had up in East Pickard Bay. And actually, this is very similar to the analysis that we did for the whole of the Southwest, where we compared our wave model to the Wavebuoys that the Channel Coastal Observatory has data for. And as you can see, the wave height and the wave period is reproduced really well by the model. We tested it over a period of a year, and it reproduces wave height to within about 40 centimeters and wave period to within about ±2 seconds. So, you know, the sort of accuracy you would expect of a high resolution wave model, certainly accurate enough for their purposes. So we're happy with that, and we're going to be working closely with them over the next 6 months or so when they plan to deploy their device to provide them the information they need. So moving on to the final case study then. This is a case study at Crantock Beach in the north of Cornwall. We're working with partners like the RNLI, the National Trust, the Duchy of Cornwall, and Crantock Parish Council. And Crantock Beach is quite an interesting case in beach hazard terms. It's got some unique features. While all the beaches, you know, along the north coast of Cornwall tend to have a hazard from rip currents and powerful breaking waves, Crantock has an additional hazard in the form of the Gannel River, which flows out across the beach face. Now, as this diagram, this rather complicated diagram shows you, on the right-hand side of those three tiles, you can see what the river did prior to around 2015. And essentially, the river used to just run straight out next to the headland at the north there. The images on the left show you what the river does now. It flows out across the beach, and it's basically cut lots of channels into the beach, which you know, you wouldn't immediately think would cause a big hazard, but actually what the lifeguards have been finding is it's very difficult to manage. People tend to get out of their depth very quickly because of these changes in the beach surface caused by the river channel. There's also sandbars where people can get cut off by the tide, and there's quite unpredictable flows due to the river channel being spread across the beach face. So the RNLI are finding it fairly hard to manage the life-saving operation at this beach, and they were quite keen to have more detailed beach hazards forecasts. So our aim was to work with them to create a safer beach. They obviously are the experts in keeping the beach safe, but if we can provide them with an extra layer of information about the hazards on a given day, that's going to help them inform their resourcing decisions. It's going to help them decide what sort of signage and messaging to put out to the general public. And overall, it could help to reduce the number of beach incidents that occur. So what we're going to do at Crantock is slightly different to the other case studies I've shown you, in that we're actually going to make the local scale wave forecasting even finer resolution. So we're going to nest a fine scale model of Crantock Beach within our big model. This model will probably be using the software XBeach, which is fantastic at reproducing rip currents, wave breaking, all those sort of hydrodynamics that you get at beaches, and has been used quite widely in the scientific literature to research rip current hazards. And that model can basically show us things like this. It can show us where waves break over shallow sandbars, which would be those yellow areas there, and also the flows that then come off the wave breaking in the form of rip currents and headland return flows. So we should be able to develop outputs from this project, which give the RNLI a really detailed look at exactly where and when peak bathing hazards will occur on any given day. Another aim of this project is to explore the avenues of getting this information out to the general public. So public messaging is, commonly done with signage and posters, but actually the efficacy of that has been found to be varied and in some cases minimal. People don't tend to spend too long looking at signs, and the general public could really do with more education prior to arriving at the beach in order to keep them safe while they're at the beach. And this, what you're seeing here on the right of the image, is actually a digital sign used in New Zealand. And so we're sort of exploring the possibility of using something similar at Crantock once we have a robust forecast that's able to predict where and when the hazards will be happening. So just to summarize then, using local scale wave forecasting where we have a quite fine model resolution really makes it possible to create these coastal applications. And if we only had those coarse resolution models, actually we wouldn't be able to differentiate the conditions from one coastal location to another, and these sort of applications just wouldn't be possible. The good news is the national scale Met Office forecasts are now at 1.5 kilometre resolution, so they're very almost at the sort of resolution we're using in these pilot case studies. And that means that if these coastal applications prove to be successful, there's the potential to roll them out on a national scale using the Met Office forecasts. And this creates lots of opportunities to develop other coastal applications, and therefore help to unlock the natural capital of the Southwest and help keep everyone safe from the coastal hazards that they sometimes pose. Thanks for listening.
What a fantastic talk. Thank you so much, Kit. That was terrific to hear. What a huge range of activities have gone on from that work. Very clear delivery of impact in lots of different and varied ways. I'd now like to say thank you very much to everyone who's presented and that we've heard from this afternoon. The talks have been absolutely fantastic, and they represent some of the most innovative approaches that SWEEP has taken to deliver the natural capital approach in the Southwest and beyond. And there's many more examples that you're going to hear about over the rest of the next few days. I hope that everyone listening in has enjoyed these presentations as much as I have. Thank you for your patience in waiting to ask questions of the team. In a moment, you're going to be able to enter the breakout rooms and ask a question or just listen to the discussions. When the option comes up on your screen, you can choose which breakout room you would like to head to first. When you get into a breakout room, you are requested to turn on your video, but to stay muted unless you are talking. You can move freely between the rooms to ask questions or just to listen into the conversations. The session will end in the breakout. So after the breakouts have been running for 30 minutes, then that will be the end of this session. So in advance, I'm going to say thank you to you all for listening in and for taking part in the breakouts, which are just about to come up. Final thing left to mention is to the people leading the breakout rooms, so that's Brett, Jonathan, Michaela and Kit. Please don't forget to press record when you go into the room. And now I think it's over to the facilitators to show us the pop-up screen for choosing breakout rooms. Thank you.